Welcome to the deep dive. Today we're tackling a book that honestly did the impossible. It took some of the heaviest topics in physics, black holes, time itself, and somehow turned them into a global phenomenon. We're diving into Stephen Hawking's A Brief History of Time. I mean, the numbers are just staggering. Over 10 million copies sold, 5 years straight on the bestseller list in London. And Hawking was clear about his mission. He wanted to address those huge human questions. What are we doing here? Where did we come from? Where are we going? But, in plain English.
Exactly. And that's really our goal for you today, to give you that synthesis. Hawking takes you on this incredible journey through scientific history, from Aristotle all the way to modern cosmology. We want to pull out the key steps, the big ideas that shape how we see the universe right now.
Okay, let's get into it then. But first things first, maybe, before the really mind-bending stuff, what are the basic rules? Like, what actually makes a scientific theory? Well, scientific.
That's absolutely the place to start because, look, a scientific theory isn't just a guess, right? It's got to do two key things. First, it needs to accurately describe what we've already observed based on a model. Maybe a few rare exceptions, but mostly it has to fit the data. And second, this is crucial, it must make definite predictions about what we will observe in the future. That's the test.
Okay, description and prediction.
But here's the catch, and Hawking really hammers this home. Theories are always provisional. You can never actually prove one is true forever. Doesn't matter how much evidence supports it. All it takes is one single experiment, one observation that consistently doesn't fit, and bang, the theory's disproven. Or at least it needs serious revision. Science is always evolving.
And you can really see that playing out in the history of physics itself. I mean, for ages, you had Aristotle and Ptolemy. Their view was the Earth is round, okay? But everything else, stars, planets, they all circled around us, perfect circles even.
Right, that was the accepted wisdom for centuries.
Then along come people like Copernicus, Galileo, Kepler, Newton, and they just flip the whole thing. They show, no, actually, the Earth goes around the sun and in ellipses, not perfect circles.
Yeah.
Complete game changer.
Yeah, and it's often those specific details that break the old model. Like Galileo, right? Aristotle thought heavier things fall faster. Seems intuitive.
Makes sense, yeah.
But Galileo actually, tested it. Showed that nope, all objects speed up at the exact same rate when they fall. Doesn't matter how heavy they are. That one finding just demolished a core part of Aristotelian physics.
And then Newton comes in with gravity, explaining why things move the way they do. But for the modern picture, we really needed Einstein, general relativity, and of course, the equation everyone knows.
EMC2.
Yeah.
Einstein really laid the groundwork for understanding the universe on the grandest scales.
And this is where it starts getting really wild, I think, because Einstein's work showed us that the universe isn't static, nothing's really sitting still, it's all dynamic, everything's in motion.
Exactly. And that directly leads to this incredible discovery. The universe is expanding. We figured this out mainly thanks to something called the Doppler shift.
Okay, like the ambulance siren thing?
Precisely. You know how the pitch sounds higher when it's coming towards you and lower when it's moving away? That's the sound waves bunching up or stretching out.
Right.
Well, light does the same thing. Light from a star moving towards us gets shifted to shorter wavelengths. That's a blue shift. If it's moving away, the wavelengths get longer. A red shift.
And Hubble.
Edwin Hubble, yeah. He observed distant stars and galaxies and found that overwhelmingly their light was redshifted. And the farther away they were, the more redshifted they were.
Yeah?
That was the smoking gun.
Yeah.
Everything is moving away from everything else. The universe is expanding.
Wow. Okay, so the whole cosmos is stretching out. But then, just as we start to grasp the big picture, quantum mechanics comes along and puts limits on what we can actually know, right? Especially about the future. Classical physics had this dream.
Oh yeah, the deterministic dream. If you could just know the exact position and speed of every single particle in the universe right now, you could calculate its entire future and its entire past perfectly.
Sounds like a plan. A very complicated plan, but still.
Well, the uncertainty principle basically killed that dream. Heisenberg showed there's a fundamental fuzziness built into reality. You simply cannot measure both the exact position and the exact velocity of a particle at the same time.
Wait, it's not just that our tools aren't good enough. It's impossible in principle.
That's the kicker. It's a fundamental law of nature. The more precisely you pin down a particle's position, the less precisely you can know its momentum, its velocity, and vice versa.
So perfect prediction is just off the table.
Fundamentally, yes. Because we can never know the exact present state of everything. We can only talk about probabilities for the future. Determinism, in the classical sense, doesn't work at the quantum level.
Okay. And speaking of that quantum level, we get down to the absolute smallest bits of stuff. Quarks.
Right. As far as we know currently, quarks are the fundamental building blocks. Protons, neutrons, the things inside atoms, they're all made of quarks.
So they're like the ultimate Lego bricks.
Sort of, yeah. And holding them together inside protons and neutrons takes incredible force. There's the strong nuclear force.
And that involves gluons. I always thought that was a funny name.
It is, but it's descriptive. Gluons are the particles that carry the strong force. They're literally the glue binding quarks together. Without them, atomic nuclei wouldn't hold together, and matter as we know it wouldn't exist.
Okay, from the tiniest glue to, well, the biggest, most dramatic events in the cosmos, the death of stars.
Yeah, when a star exhausts its nuclear fuel, gravity starts to take over. What happens next really depends on how massive the star is. There's a key threshold called the Chandrasekhar limit.
Chandrasekhar limit, right.
It's about 1.4 times the mass of our sun. If the star's core, the remnant left after it burns out, is below this limit, it can stabilize. It might become a white dwarf or maybe a neutron star, incredibly dense objects, but stable.
But if it's heavier than that limit,
Then gravity wins. Completely. There's nothing strong enough to stop the collapse. The star implodes under its own weight, crushing down into an infinitely dense point, forming a black hole.
and that's where gravity is just overwhelming, so strong that nothing can escape, not even light once it crosses a certain boundary, the event horizon.
Exactly. The event horizon is basically the surface of the black hole, the point of no return. Cross that line, and according to classical physics, you're trapped forever.
And this was one of Hawking's biggest contributions, right? He showed that black holes aren't actually perfectly black, they leak.
That's Hawking radiation. It was revolutionary. Due to quantum effects right near the event horizon, pairs of particles can pop into existence. One falls in, the other escapes. To an outside observer, it looks like the black hole is emitting particles like X-rays and gamma rays.
Which means they're not actually permanent, they shrink.
Very, very slowly, yes. Over absolutely unimaginable timescales, they actually evaporate. Which, by the way, leads to a huge puzzle called the information loss paradox. What happens to all the information about the stuff that fell in? Still a hot topic.
Okay, so that's the fate of stars. What about the whole universe? The beginning. The Big Bang. The book mentions a few different takes on that singularity event.
Yeah, there's the standard hot Big Bang model, which is the baseline. But Hawking also delves into deeper questions, like using the anthropic principle.
The anthropic principle, that one feels a bit philosophical.
It is, definitely. It basically argues that the reason the universe has the specific laws and constants that it does values tune just right for stars, planets, and life to form is because, well, if it didn't, we wouldn't be here to observe it in the first place.
So we see it this way because it's the only way we could see it being here.
That's the gist of the argument. It's a bit controversial, but it tries to tackle that why these laws
Yeah.
question.
Right.
Okay, shifting gears again. Time itself. This is maybe the most slippery concept. Hawking talks about 3 different arrows of time.
He does. And what's fascinating is that the fundamental laws of physics, things like gravity or electromagnetism, they don't actually care which way time flows. The equations work just fine forwards or backwards.
But we definitely experience time going in one direction.
We absolutely do. Hawking says this directionality comes from 3 arrows. First, thermodynamic time, the direction in which disorder or entropy increases. Think of a broken cup. It doesn't spontaneously reassemble itself. Disorder increases.
Okay, second law of thermodynamics.
Yep. Then there's psychological time, the direction we perceive time flowing. We remember the past, not the future. That gives us a strong sense of direction.
Makes sense.
And finally, cosmological time, the direction in which the universe is expanding. Since the universe is currently expanding, this arrow points forward along with the others. If the universe were contracting, this arrow would point the other way. So these 3 arrows align and give us our sense of forward-moving time, which inevitably leads to the question, can we travel against the arrow? Time travel.
Ah, yes, the fun stuff. Based on Einstein's relativity, the book outlines 2 theoretical possibilities. One is traveling faster than the speed of light.
Which current physics says is impossible, right? The cosmic speed limit.
Correct. Relativity puts a pretty firm block on that.
Mm-hmm.
The other possibility, though, is finding or maybe even creating a wormhole.
Like a tunnel through space-time.
Exactly. a shortcut connecting two very distant points in space, or even two different points in time. It's theoretically allowed by general relativity under certain very exotic conditions. Some physicists speculate we might one day figure out how to make one.
Wow. That's, yeah, mind-bending.
It is. But even if time travel is possible, Hawking includes a fun little warning about potential hazards, specifically concerning antimatter, matter's opposite twin.
Right, like positrons instead of electrons.
Yeah. He basically says, if there are anti-worlds out there made of antimatter, and you happen to meet your anti-self, don't shake hands. You would both vanish in a great flash of light. Annihilation.
Okay, note to self. Avoid shaking hands with my antimatter doppelganger. Good advice. This all leads us, though, to the ultimate quest mentioned in the book, right? The search for the unified theory.
Yes, the holy grail of physics.
Yeah.
Because the big problem we have right now is that our two most successful theories about the universe fundamentally clash.
General relativity and quantum mechanics.
Exactly. General relativity describes gravity and how large things behave. Planets, stars, galaxies. It works beautifully on big scales. But it completely breaks down at the tiny scales of quantum mechanics or inside singularities like black holes or the Big Bang.
And quantum mechanics.
It's fantastic for describing the subatomic world, the forces acting on tiny particles, probabilities. But it doesn't currently include gravity in a consistent way with the other forces. Electromagnetism, the strong and weak nuclear forces.
Yeah.
They just don't talk to each other properly in the math.
So we have two amazing theories that work perfectly in their own domains, but they can't describe the whole picture together.
Precisely. So the ultimate goal is to find one single theory, a unified theory, or a theory of everything that combines them both. A theory that explains all forces and all matter, from quarks to cosmos.
And the leading candidate discussed in the book, at least at the time, was string theory.
That's right. String theory was, and in many ways still is, the most promising framework for unification.
Okay, string theory. This is where my brain usually starts to hurt because it involves extra dimensions, a lot of them.
That's the really challenging part. Instead of particles being zero-dimensional points, string theory suggests the fundamental constituents of reality are tiny, vibrating one-dimensional strings. And for the math to work out consistently, especially to incorporate gravity, these theories often require more dimensions than the four we experience: 3 space, 1 time.
26 dimensions, the book mentions.
Some early versions needed 26, yeah. More modern versions, like M-theory, often settle on 10 or 11 dimensions. The idea is that the extra ones are compactified, curled up incredibly small, so small we just don't perceive them in everyday life.
Still pretty mind-boggling. It shows how difficult this unification problem really is.
Absolutely. And Hawking, looking at this grand quest, lays out 3 possible endings for it.
Okay, what are the options?
Option 1, we actually find it, a single, complete, consistent, unified theory. The end of the search, in a way.
Option 2.
We find that there is no single theory. Maybe there's just an infinite sequence of theories that get progressively better, describing the universe more accurately. But we never reach a final one.
And the third?
Option 3, maybe there's no theory at all in the predictive sense we want. Maybe events are fundamentally random or arbitrary beyond a certain point, and a complete predictive theory is impossible.
Wow. So triumph, endless refinement, or fundamental limits?
Pretty much. But Hawking seemed hopeful for the first option. And he wrote quite powerfully about what finding that complete theory would mean.
Yeah, that final quote is really something. Can you share that?
Sure. He wrote, "If we discover a complete theory, it should in time be understandable by everyone. Then we shall all be able to take part in the discussion of the question of why it is that we and the universe exist. It would be the ultimate triumph of human reason, for then we should know the mind of God."
Know the mind of God. That's
Yeah.
quite a statement. It really captures the scale of the ambition.
It does. And think about the ground we've covered, just tracing his outline from Aristotle thinking the Earth was the center, through Newton's laws, Einstein's curves, the fuzziness of quantum mechanics, black holes that aren't quite black, all the way to vibrating strings and hidden dimensions. It's an incredible intellectual journey.
It really is. It gives you a map of reality as we currently understand it, highlighting both the amazing things we do know and the huge mysteries still out there on the frontiers.
And the quest continues, doesn't it? That search for the ultimate rules, the unified theory, is what drives so much of fundamental physics today. It keeps things moving.
Which kind of brings us to a final thought for you, the listener, inspired by the book itself. Even if scientists do eventually find like one perfect unified theory, that beautiful set of equations, it's still just equations on a page.
Rules and logic, yeah.
So the question Hawking leaves us with is this. What breathes fire into the equations? What takes those rules and makes an actual living, breathing universe for them to describe? It's that gap between the how and the why of it all. Something to ponder.